Hello, my name is Lisa Shrestha, and I'm a PhD student in the Graduate School of Biomedical Sciences at the University of Alabama at Birmingham. And today I'll be talking about identifying circular RNA and the sequence-based rules underlying back-splicing junctions. So circular RNA are a subclass of long non-coding RNAs that are characterized by their circular structures. They are formed by a mechanism called back-splicing mechanism, where the downstream 5' end is covalently linked to the upstream 3' end. The lack of free ends in these circular RNA make them much more resistant to exonuclease degradation compared to their linear counterpart. The drivers of back-splicing mechanisms and circular RNA biogenesis are still not completely understood. However, there are two hypotheses that have been proposed for circular RNA biogenesis. The first states that presence of inverted complementary sequences in the flanking introns promotes circularization. And the second hypothesis suggests that circular RNA can be formed by lariats that are formed as a byproduct of canonical splicing or that are formed during exon skipping in alternative splicing. Several read-based as well as transcript sequence-based tools have been developed to identify circular RNA. In this project, we have explored several physiochemical properties that have not been studied in context of circular RNA and have utilized tree-based classifier to develop a machine learning tool that can accurately identify circular RNA. Moving on to the methods, we first started by curating a data set that consists of circular RNA and mRNA sequences. For the purpose of this project, we specifically focused on 50 nucleotide long sequences surrounding the start and end site of each transcript, giving us a 100 nucleotide long sequence for each RNA. Then we extracted feature values from these sequences based on these 5 different physiochemical properties, namely nucleotide chemical property, enthalpy, entropy, free energy, and stacking energy, where nucleotide chemical property was mononucleotide features in which each nucleotide was assigned a unique 3-digit code based on their chemical properties, like ring structure that they have or the hydrogen bond strength that they have. The other remaining 4 physiochemical properties were dinucleotide features whose values were obtained from a database called KN index. So once we had feature matrices for each of these different physiochemical properties, we used it as an input for our classifiers. So we used 2 different classifiers for this project. We used the decision tree classifier, and we also used the XGBoost classifier to predict if a transcript is a circular RNA or if it is a non-circular RNA. As a validation, we also used a different data set from a previously published study called JEDI. So JEDI is a circular RNA identification tool that uses deep learning algorithm to predict circular RNA. So as a validation, we use the data set that they have used to analyze the performance of their tool. And we used their data set in our algorithm to predict circular RNA. So moving on to the results, we were able to achieve high accuracy for circular RNA prediction with all the different physiochemical properties that we implemented. The highest accuracy we were able to achieve in our data set was 94.49%, while using the XGBoost classifiers with the nucleotide chemical property feature matrix as an input. Even while using the decision tree classifier, which is a fairly simpler binary classification model, we were still able to achieve an accuracy of 86.5% while using the stacking energy feature matrix. Even for our validation dataset, that is the JEDI dataset, while using a combined feature matrix of the nucleotide chemical property and stacking energy feature matrices, we were able to achieve the accuracy of 97.8% for predicting circular RNA while using the XGBoost classifier. So these observations indicate that physiochemical properties of the nucleotides directly surrounding the splice site can predict circularization of a transcript sequence with high accuracy while using interpretable tree-based machine learning classifiers. So for future directions, we will be looking specifically into each of these physiochemical properties based on the positions of importance in the 100 nucleotide long sequences. And a long-term goal would be to incorporate this tool as a part of a circular RNA identification workflow to identify or validate novel circular RNAs that were predicted from a general circular RNA identification workflow. Thank you for listening to my talk. If you have any questions, please feel free to email me or post comments on this website. Thank you.